So it's my pleasure to have Professor Cheng Lie here. He's an assistant professor of uncertainty quantification at the University of Potsdam. And he's a project leader in the Collaborative Research Center SFB 1294 on data assimilation at the University of Potsdam. Previously, he obtained his doctoral degree in mathematics in 2016 at Freie Universität Berlin, and his research focuses on the mathematical theory of Bayesian inverse problems, including approximate Bayesian inference, probabilistic methods, and maximum a posteriori estimators. So I'm happy that you followed our invitation, and I'm happy to hear your talk.
Thank you very much. Should I turn this on, I guess?
Check.
Hello? Yeah, yes, now it's perfect. On. Okay. So thank you very much, Alex, for the introduction. Thanks, especially to those of you who made it here on this wonderful Thursday morning. Yeah, so I would like to begin, before I start this talk, I'd like to just acknowledge a few people. I'd like to organize the organizing team for the summer school. It was really very useful to have these signposts from the S-Bahn to here. Otherwise, I think I would be lost. So I really appreciate that, and whoever put those up. But of course, organizing a summer school like this takes a lot of people. So thanks to all of them, even if I haven't met them. I'd like to thank the people who invited me, so Professor Katja Ickstadt and Alex, and the people who really got in touch with me at the beginning and helped sort out administrative things. So Mr. Zhou Yiting, Ms. Marion Zur, and of course, Jens. But thanks to everyone who made this possible. And before I begin, I'd like to temper the expectations about this. So this is a school about machine learning, and I must be very frank with you. I don't think I would be considered a real machine learner. I'm a mathematician by training, as Alex mentioned. And so today's talk will mainly be more, you could say, abstract and conceptual. I won't talk about any particular algorithm, but I'll try and talk about some ideas, some mathematical ideas that really, in my opinion, underpin a lot of algorithms for inference. Okay, so let me begin with the motivation. In my view, and this might be wrong, so some common uses of machine learning are to build some model of an unknown function that can explain some observed input-output pairs. So nature or some measurement device gives you input-output pairs, and a basic question in applied anything basically is to say, can we use this data to predict what's going to happen if we observe a different input? Can we predict what the corresponding output would be? And of course, so there are two parts to this, right? We first need to build the model, and the next thing is we need to use the model to predict the output for new inputs that we haven't observed yet. So that's how I approach machine learning. That's what I think of machine learning. And if you disagree, I welcome your disagreement. What do we need to do in order to use machine learning in this way? Well, first of all, the really fundamental thing that we need to do is we need a way to represent incomplete knowledge. So if you consider the space of all models in the universe that can explain a fixed number of input-output pairs, I hope you can see that this space is really large, right? It's much larger than the set of input-output pairs that you have, which is finite. So first, we need a way of representing incomplete knowledge. And the second thing is that we need to have a way of updating this knowledge when we acquire new information. We never stop at just the data we have. We always try and say, let's try and collect more data. Let's try and verify our model, test it. So we're always acquiring new information. It doesn't just stop at one data set. So we need a way to update our state of knowledge about something that we don't know. And the third thing is, and this is really the topic of this school, is how do we perform this update step in a computationally efficient way? I think it's really great that now in machine learning, people are, well, it's not now, I guess this SFB has been doing it for almost 12 years, but how to do this inference basically in an energy efficient way. It's really fitting that Dortmund used to be a coal mining town. As you know, energy is a very hot topic right now. So it's really important to do inference in a way that respects some physical limits, so to say. So this is the outline of the talk. The talk will be divided into two parts. I think I will, depending on how I go, I'd like to have like a short break in the middle so that we can clear our heads and get a bit of fresh air. So the first part will be divided into a really quick overview of probability theory, Bayesian inference, and Bayesian inverse problems. And the second part will be going more into really the focus of this talk, which is, first, I'd like to give some motivation for randomization. This talk is about randomized Bayesian inference. So first, I'd like to explain why are we doing any randomization at all? And then I'd like to close with some theory about randomized Bayesian inference and an example of randomized Bayesian inference. And the example is maybe where there will be something that is closest to an algorithm. So that's really the place where there's something that could be considered an algorithm. And for those of you in the lecture hall, if at any point something is unclear or you cannot hear me, please just raise your hand and let me know, okay? All right, so let's begin. What's a probability space? I like to start with this because this is for me really the foundation of statistical inference. You can't have statistical inference without probability theory, and you can't have probability theory without a probability space. So what's a probability space? It's a triple. So it's a collection of three objects, omega, f, and p. Omega is some non-empty set. Sometimes we call it a sample space, but that's really not a good terminology in this case because samples often means data. So let's just call it omega. F here is what is known as a sigma algebra of subsets of omega. And now we don't need to go into the definition of what a sigma algebra is, but it's important to note that it's a collection of subsets of omega, but it's not always the collection of all subsets of omega. That collection is sometimes known as a power set. And that's basically the best sigma algebra that you could possibly ask for. But it's basically a collection of subsets of omega that respect certain rules. Okay, so if you're familiar with sigma additivity, that would be one rule, for example. And third, we have p. P is a function from this collection, this sigma algebra, to the closed unit interval. So if I write 0, 1 here, that's the set of all numbers from 0 to 1, including 0 and 1. And I call this the closed unit interval. And p is a probability measure. So it's a function from f, a sigma algebra, to the closed unit interval. What this means is that you give p a set in the sigma algebra, and it will give you a number between 0 and 1. So what's a sigma algebra? It's a collection of what is known as sometimes events. So the term events comes from probability theory, and I understand it might not be used uniformly in the same way across all disciplines, but I'll just refer to them as events. So any element of a sigma algebra, which is actually a subset of omega, that's an event. And the sigma algebra F here, what it does is that it represents, to some extent, an information resolution. And I'll try and explain what that means in a short while. So here's an example, a very simple example. Let's consider the random experiment. You take a coin, you toss it, and you see what is the outcome. Is it heads or tails? And I'll map heads to 0 and tails to 1. Okay. So here, my set omega just consists of two things, 0 and 1. What's the least informative sigma algebra on this set? The least informative sigma algebra is the sigma algebra that consists of two subsets of omega, the empty set, which contains nothing, and omega, which contains everything. And why is this the least informative sigma algebra? You can think of this as saying that this sigma algebra, with this sigma algebra at this information resolution, the only thing you can say is that nothing happens, so that's the empty set, or something happens, which is omega. Okay, and hopefully you can persuade yourself that with this sigma algebra, you can't really say very many interesting things, right? Either nothing happens or something happens. Yeah, of course. What's the most informative sigma algebra in this case? Well, it turns out with sigma algebras, you always have to have the empty set and the whole set. So that's what we do. But now we go a little bit, we have more detail. We can ask more detailed questions. And so for this most informative sigma algebra, we can either say that it comes up heads, so we have the outcome 0, or we have the outcome tails, 1. Okay? And with such a simple set, this is the most informative sigma algebra because this is actually the collection of all subsets of omega. You can't get better than this. So this is what I mean by a sigma algebra being like an information resolution. You have some set, and the sigma algebra dictates to you what kind of questions you can ask from using this sigma algebra. In practice, the sigma algebra is not so, I guess for many machine learning tasks, the sigma algebra is given. You get it for free. But I bring this up because it's actually quite important. Whenever you're doing probability theory, you're always working with the triple, and each element of this triple is actually really important. So much for the sigma algebra. Any questions? Okay. So this is what we saw from the beginning. What's a probability measure? I'm going to abbreviate a probability measure as PM. And a PM, or a probability measure, it quantifies the certainty of some event that you give to the probability measure. Remember, the probability measure is a function from the sigma algebra to the closed unit interval. So you give it a set and it gives you a number. So one example is the statement, it will rain tomorrow with probability 0.9. So note that I'm using numbers in 0 to 1 instead of percentages. What does this mean? This means that using this implicitly, we're working with a probability measure that tells us how certain we are that an event will happen. And the certainty of this event is related to some completeness of knowledge. Like how much knowledge or information do we have about something that we're interested in? And this certainty is described, we describe it using the probability measure. So here's a really nice fact that I would say actually makes statistical inference possible. Given a tuple, so just two objects, omega, a non-empty set, and a sigma algebra calligraphic F, there are many possible choices of probability measure that you can put on this. So recall from the previous slide that a probability measure quantifies the certainty, how certain we are about some input event that we give it. If there are many possible choices of a probability measure, this means that different probability measures can assign different probabilities or different certainties to the same event that we give it. So here's an example. We take again the example of a coin toss. And since we know that the least informative sigma algebra is not really useful, let's use the most informative sigma algebra, when we can tell if it's heads or tails. And now let's consider the first probability measure, P1. So what P1 does is that it assigns to the event that we have heads, probability 0.5. And it assigns the same probability to the event that we have tails, so the outcome 1. What can we say about P1? We can say that it represents the state of knowledge where we have maximal uncertainty. Basically, both outcomes 0 and 1 are equally possible. We can't say that one is more likely than the other. Okay. What about P2? So in P2, assigns to the event 0, so we have heads. The probability is 0.001. And to the outcome where we have tails, so the outcome 1, probability 0.999, which is really close to certainty. So P2 represents a state of knowledge whereby we are really more certain about what's likely to happen. In particular, outcome 1 or the outcome tails is more likely to happen. So we're much more certain. And the key idea, which will really come up in a lot of what I'm going to talk about, is that we use different probability measures to represent different states of knowledge. And in particular, whether if we're more certain or less certain about certain things. So really the key thing underpinning everything will be a probability measure. Okay? So in applications, maybe you're more familiar with working with random variables. So I'll abbreviate that as an RV for simplicity. It's more natural in many cases to work with random variables instead of probability measures. So what's a random variable? Just to fix terminology, we have a fixed probability space consisting of 3 objects. And now, in addition to this, let's specify a non-empty set E and a sigma algebra calligraphic or script E of subsets of the set E. Now recall that the way to understand a sigma algebra is that it represents some kind of information resolution. What are the questions that we can ask about some random variable? Okay. What is an E-valued random variable? Let's call it X on some probability space. It's simply a function, X, that maps any element in omega to an element in E, with the additional constraint that this function has to be so-called FE measurable. I won't state what it means precisely, but I'll tell you what it implies. So measurability implies that basically we can compute the probability that X belongs in subset S for any S that belongs to the sigma algebra on E. Okay, and this is a really basic task, right? If you have a random variable, you want to ask, what is the probability that this random variable will lie in a certain range of values? And measurability basically allows us to even compute such quantities. Now I'm going to use the term law in a lot of this talk. What is the law of an E-valued random variable? It's a probability measure. Let's say we have a random variable X. The law of X is a probability measure, Px, on this tuple, so this pair consisting of a non-empty set E and the sigma algebra on E, whereby basically the probability measure Px assigns to any subset S simply the probability that the random variable X is in S. And we can do this because X is measurable. So we can actually, these quantities can be computed. Okay. So what's the key idea here? We started off with saying that probability measures are really the essential tool that you're working with whenever you do statistical inference. On the other hand, in applications, you often work with random variables. But the good news is that whenever you have a random variable, you have a probability measure, namely the law. Okay, so there's a nice correspondence between random variables and laws. I'm sorry, and probability measures. Okay, any questions so far? Yes.
So actually my question is calligraphic F always the Weierstrass P of omega?
No, calligraphic P does not always have to be. Calligraphic F doesn't have to be the power set of omega. Okay. It can be something finer, or coarser, I should say. You can't get any finer than the power set.
Okay, thank you.
You're welcome. Okay, so in basically all machine learning tasks, you're going to have more than 2 random variables. There will be more than 2 quantities that you are measuring simultaneously, and you want to explore some relationships between them. So an example, if you're going to do the hackathon later, is image-based virus detection. What are 2 variables here? The first one is a particle that we see, is it a pathogen or not? And the second variable would be, what does this particle look like when we look at it through a sensor? We can model these variables as random variables, because typically it's not just one, we can't just catalog, well, in the case of pathogenicity, we can, it either is or isn't. But if you try and catalog all possible images, that's really going to be hard. So we can, and besides, nature often gives us different images, right? We can take a particle and image it, but we can't predict ahead of time what it's going to look like. So these outcomes, these images, you can view them as random variables. So we will model both of these things, pathogenicity and what the particle looks like, as random variables. X1 will be our pathogenicity random variable. It maps from some probability space omega to E2, where E2 is a simple set 0 or 1. 0 is it's not a pathogen, 1 is it is a pathogen. And X2 is again a random variable on a probability space that takes values in E1. And what is E1? You can think of E1 as the set of all possible images that a given sensor can produce. So you just quantify all the possible pixels in the output and how many values per pixel you can have. Whatever the image produced by your sensor is, it will be in this set, right? So this notation E1 times E2, this is like a cross product of sets or product of sets. This just is the set of all pairs little e1 and little e2, where e1 is in big E1 and E2 is in big E2, okay? Now, given 2 random variables, 2 or more random variables, we'll stick with 2 for now. The joint law of x1 and x2 is a probability measure P subscript x1, x2 on this set E1 cross E2. Okay, sorry, that's a little bit fast. Did everyone get that? Okay, so it's basically we take 2 random variables, we combine them into 1 random variable, and we can do the same trick that we did before. We have a random variable, it has a law. So the joint law just means that you basically break up your random variable into multiple components, and you call that the joint law, the joint law of that random variable. Okay, just to recall what we saw from the previous slide. Now, given a joint law of 2 or more random variables, we can ask questions about what are the marginals. Okay, so the marginal law of x2, given this joint random variable x1 and x2, is a probability measure px2, whereby if we give it the set S2, that's simply the joint law of the product E1 times S2 for any S2 in the sigma algebra E2. And Px2, this marginal law of x2, is a probability measure on this tuple, a non-empty set E2 and the sigma algebra on it. So how do we interpret the marginal law? We basically say we obtain the marginal law from the joint by saying we don't care basically what values x1 takes. We only care really what values x2 takes. In this sense, we say that we marginalize out x1. We can do the same thing to compute the marginal law for x1 as well. So in the example of image-based virus detection, what is x1? X1 is the marginal law of pathogenicity. In this case, it's not really interesting because it either places mass on 0 or on 1, or a combination of the two. Px2, on the other hand, is a little bit more interesting. It's the probability distribution of images. And if you think about that, that's not a priori a very easy probability distribution to work with, because the set of all images that your sensor can produce can be quite complicated. So here's a very fundamental question, which is really basic. Suppose that we have two random variables, x1 and x2, and we know, for whatever reason, that the second random variable takes a certain specific value, little x2. We can then ask, what's the probability that the first random variable takes values in some set S1? Mathematically, what this corresponds to is saying, what's the conditional law of x1, given that we know that the second random variable equals little x2? Again, in the example of image-based bias detection, we can reformulate this as saying that given an image x2, we're given an image of some particle, we would like to know what's the probability that this particle that we've imaged is actually a pathogen or not. So the intuition, which maybe some of you have seen from a first course on probability theory, is that for any, let's say, for any event S1 in the sigma algebra E1, the conditional probability that the first random variable x1 takes values in this set S1, given that we know that x2 has a specific value, little x2, is given as follows. So this is the conditional probability that we're interested in. And we basically take the ratio of the joint law of S1 cross x2, divided by the probability of the marginal law of x2, basically, okay? And the intuition of this is that once you know that x2 is the random variable is equal to little x2, this kind of tells you where to focus your probability accounting on. So we look at this set and then we do all of the computations with respect to this set. So some remarks, as you might have seen, for this formula to make sense, we need the denominator here to be positive. You can't divide by 0, it's really a bad idea. And this formula is actually, it makes sense when we're looking at discrete, when x2 is a discrete random variable, okay? In more general cases, you can prove formulas like this, which are similar, and you can make this rigorous as well. Well, what's the key idea I'd like you to take away from this slide is that the conditional probability measures are what we use implicitly to describe a state of knowledge with incomplete information. So we have some random phenomena, and through some measurement, we know something about this random phenomena, but we don't know everything. So can we use that information to state something about what we don't know? And for that, we use conditional probability measures. Okay, so that's the end of the first part. And the second part will be about Bayesian inference. Before I move on, are there any questions? Yes.
So I'm wondering whether P subscript of x2 could be, for example, the frequency on how they use
So frequency, you can understand that as that leads to the concept of a histogram, right? And eventually, if you were to refine your histogram, your bins further and further, under some assumptions that would correspond to a density, a probability density function. And yes, you can think of the probability density function can correspond to px2. But in this case, px2 really here is a probability measure. So as some of you might know, not all probability measures have a density. But whenever you're working with a random variable, you will always have a probability measure, but you might not have a density. But in some, yeah.
So what does P of x2 then represent?
This quantity here,
yeah.
This represents the marginal law. So it's a probability just of x2. We have x1 and x2 as a joint random variable, but we're only interested in the probability that x2 belongs in some set, for example. And for that, we use px2. Okay. Think of the marginal law as basically the probability measure that is associated just to x2. It ignores everything about x1. Okay. Thanks for the question. Okay, so now let's go into Bayesian inference. For the last slide, we needed to assume that, well, if we assume that this quantity is positive, then the conditional law of x1 given x2 is shown here. Now, what we can do is really basic, right? Let's choose x1 to be the set consisting of just one element, little x1. Okay, and now we can basically multiply both sides by the denominator. And what we get is this equation. So the product of the conditional law with a probability that x2 is little x2, that's this joint probability. Okay. Now we can do the same thing if we look at the reverse conditional probability. Assuming that this quantity is positive, we have this formula. So you'll notice that the right-hand sides of this equation and this equation are the same. So we have this equality here. So it's a product of a conditional law with a marginal law and the flipped conditional and marginal. So this is what we saw from the previous slide. Now we're going to divide by p of x2 equals little x2 to get the base formula for this conditional. So this is base formula. Okay, let me walk you through it. What we have here is the conditional of x2 given x1. Okay, so if we have some information about x1, what can we use to say, how can we use it to say something about x2? And here we have the marginal law of x2, and here we have the marginal law of x1. And if we have these three ingredients, we always have the flipped, the other direction of the conditioning. Okay, the conditional probability measure of x1 given x2. So the useful thing about Bayes' formula is that if you have one conditional law and the two other marginals, you can always get the other conditional. Again, using the example of image-based virus detection, given that x2, the conditional probability measure of x2 given x1, that's the conditional law of an image, given that we know that x1 is or is not a pathogen. So it's like saying, if we know that the particle is a pathogen, what will it look like in the sensor? And the other direction, the x1 given x2, that's the conditional law of pathogenicity, given that we see what the particle looks like, right? And that's really the task, I believe, of the hackathon, is that here's a bunch of pictures of particles. Can you tell which of these particles are pathogenic or not? So here's Bayes' formula again. And I'm highlighting in red x1 because I'd like to emphasize that this conditional is actually a probability measure on x. And how we get this probability measure on x is by first using this conditional, which is actually conditioning on x1, and we divide it by some quantity that doesn't depend on x1, and then we multiply by a probability measure again of x1. So you can think of this as saying that the left-hand side is a probability measure with respect to x1. And we get it by multiplying a function of x1 with another probability measure on x1. So in the terminology of Bayesian inference, P of x1 is known as the prior law of x1. It's what we know about x1 before we take any information into account, before we do any conditioning. So it represents our state of knowledge about x1 before we observe anything about the other random variable x2. P of x2 given x1, so that's the numerator here, that is known as the likelihood of the random variable x2, given that we know something about the other random variable x1. And P of x2 being equal to little x2, that's sometimes known as the evidence contained in this observation. Now, what about the left-hand side? That's a really important quantity in Bayesian inference. That's known as the posterior. That's the posterior law of x1 given x2. So we know that conditional probability measures capture our state of knowledge or our certainty about something given in the presence of incomplete information, right? So the posterior tells us the state of knowledge about the unknown quantity after we have observed something about x2, okay? So we can basically rewrite in words this formula above as saying that the posterior is equal to the likelihood divided by the evidence times the prior. And if there's one formula which hopefully you remember from this lecture, it's this formula. You don't have to remember the mathematical symbols, just remember what Bayes' formula is. Okay, so here's the formula again. Some remarks. The evidence is in practice really difficult to compute. In many problems of real world relevance, the evidence is really hard to compute. And for this reason, sometimes it's said to be intractable. So think of the example, what's the probability that the image of a particle is a given image? I give you an image, right, that's produced by a sensor, and I ask you, can you tell me what's the probability that I give you a particle, you put it through the sensor, and the sensor gives you this image. What's the probability of this image being produced? That's quite hard, because in principle, you would have to look at all particles that you can put in the sensor, look at all of them, and then quantify the probability that this given image occurs. That's quite hard, right? And in many cases, the posterior has no closed form expression. By this, I mean, you can't write down a formula for the density. And this is really the rule in Bayesian inference. You can't say that the posterior has some nice density that we know. We just need to specify some parameters. That rarely happens. So an important consequence of this is that to sample from the posterior, what we need to do is that first we need to draw samples from the prior distribution, reweight using the likelihood. So if you're familiar with importance sampling, in some ways we are doing importance sampling. And the thing that we're using to do importance sampling is the likelihood. Anyway, the key thing here is that for a Bayesian statistician, or if you're doing any Bayesian inference, the posterior is the best thing you could produce. It's the thing that you use for statistical inference after you have data. And the key thing here that I'd like you to take away from this slide is that the posterior, you can think of this, I did programming a long, long time ago, so forgive me if this seems very simplistic. Think of a code, and the code outputs a posterior, and the function is called Bayes. And the inputs that you need to give to the function Bayes are the prior, the likelihood, and the data. Okay, so this is what I'd like you to take away from this slide. Okay, so much for Bayesian inference. Any questions about that? Okay, now we can move on to inverse problems. So here's a bunch of math. Suppose we have an equation, that y star is equal to g of x star plus epsilon star. Okay, what's what here? Y star lives in some space, some set calligraphic y. We call that the data. G is a function from some set x to y, and it's a fixed deterministic function, which we sometimes call the forward map. And I'll explain why this is a forward map in a short while. X star lives in the set x, and it's what is known as the unknown parameter, or simply the unknown. And epsilon star is a realization of some random variable that takes values in y, and this is called observation noise. And it's basically our admission to the fact that there is no perfect measurement device. Every measurement device will have some flaws, will be sensitive to environmental conditions, and these will introduce noisy artifacts. What's an inverse problem? An inverse problem is, given data y star, given an observation y star, and this observation model, find the parameter, the unknown x star, which actually generated that y star. So this is the inverse problem, and it's inverse because the forward problem is, given x star, evaluate y star. Okay, so I hope you can see the direction here. So in the next few slides, I'm going to give you two examples of inverse problems. I believe earlier in this week you saw there was one lecture on inverse problems, but I'll give you just two examples to make this lecture somewhat self-contained. So the first example will be about computerized tomography, and the second example will be maybe more relevant to machine learning because it's about non-parametric regression. And I hope to explain to you why maybe non-parametric regression is what many machine learners are doing. Okay, so what about CT, so computerized tomography? What is the data y star? Some of you probably know this, but for those of you who don't, this is the schematic of what's happening when you do a CT scan. You have a patient here, and they're lying on a bed in orange, and this bed is passed through a cylinder. And in the cylinder, you have basically a rotating device. And on one side of the device, you have basically a bank of X-ray detectors. And at one point, on the other side of this arrangement, you have a source of X-ray beams. So the X-ray, the source diffuses some X-ray beams out, they pass through the patient, and they are each contained into they're collected at a number of detectors. Then this whole device is rotated within the cylinder, such that you don't just get one snapshot, so to say, in this alignment, you also get different snapshots of the patient. Okay, Gesundheit. So what's the data here? Y star will be a vector, y star consisting of components y star I, where I goes from 1 to d. So in this sense, our space calligraphic y is just a set of all real numbers, all the set of d vectors, basically. And d here, think of this as the number of detectors. What's yi star? It's actually quite a complicated object because this yi star, the single real number, is the integral of a specific function along the line traced out by the X-ray beam as it goes from the source to the detector, to each detector. So as we know, X-rays are light. Light travels in straight lines unless you're in relativity theory. And on this line, there's a function, which is basically the function that describes what does the patient look like. What is the density of the material as the ray passes through the patient? Okay, and you integrate this function over the X-ray beam as it passes through the patient. And you do this for every detector. That gives you D numbers. What's the unknown? Well, this is not actually the unknown. This is the inferred unknown. The unknown is ideally what we would like to do if we're doing imaging or CT scanning is we would like to be able to see what a patient looks like at a cross section, right? But you can't do this without harming the person, and we don't want to do that. So we do the next best thing. We solve an inverse problem. And the unknown here is basically a density profile of the different substances of this cross section of the patient. So this is, maybe the inset is a little bit small here, but this white line tells you where the cross section is. It's around through the heart, okay? And the darker regions basically indicate regions where the density is really low. So maybe you can guess that this is some kind of abdominal cavity, maybe the lungs. And the white regions are where the density is really high. So this is probably bone, where the ribs are being imaged. And this is the heart. So this is being done regularly in medicine, in hospitals. This is a really important tool that people now have for non-invasive surgery or deciding non-invasive procedures, basically. So again, just to recall what the data and what the unknown are here, what's X? If our unknown is basically something like this, if we could see what the patient looks like, the space X of unknowns is basically the space of density fields, an image, right? What does the patient look like if we could just cut them in the cross section? So the inverse problem here is, as usual, given data, so this vector RD, try and infer what the patient looks like at this cross section. What are some challenges here? Well, the dimension of X, if you think about this, if you want to have a really high resolution image, because you're going to use this image to decide where do we operate, what do we need to look for, what do we need to take out, you want this image to be really precise, right? So the more precise it is, you need more pixels. So the more pixels you have, the higher dimensional X will be. Furthermore, the forward model, which tells you what the patient looks like and then produces the vector Y of real numbers, which correspond to these integrals. This is actually a really complicated forward model. I could write it down, but I don't want to because it's rather ugly. And evaluating this model for a single X can be really expensive. So those are two challenges specific to CT, you could say, or that are specific to CT. But for inverse problems, there are two challenges that almost always appear. One is that the observations are noisy. Okay, we don't know what G of X star is because there's noise, and we don't know what the value of the noise is. Furthermore, the function G itself is non-invertible. What this means is that you can have two different inputs, you give them to G, and G will give you the same output. And in many cases, you can have more than two. You can have many different types of inputs that will give you effectively the same output. And on top of this, you add noise, so you don't exactly know what the output is. So these are two challenges to inverse problems that actually make inverse problems really difficult. Okay, so that's the first example. The second example is non-parametric regression. So maybe, I think all of you are more familiar with this than I am. You're given some input-output pairs, or you're given some two variables. One you think of as being like an ordinate or some input variable, and the other you think of being as a response variable. So UI and VI. And you want to model these input-output relations, input-outputs through some function that you can then use to do predictions. So for this, we are implicitly assuming that every output VI is the product of some input UI through some unknown function F star plus some noise eta I. And we have n of these. And we assume that there exists a true F star which can actually do this. This assumption is not always justified, but we do it because sometimes that's what is expected, right? So what we're seeing in this plot here is that each red dot, think of that as an input-output pair. So for this red dot, we have this input and we have the output close to 0. For this one, we have a much different input and we have a very similar value, so on and so forth. And what we're seeing in those blue shaded regions, think of them as confidence intervals of where could this unknown function be. I want to know what F star is because I want to predict what the output will be if I give a different input. Okay, so probably some of you have already done Gaussian process regression. This is a picture of Gaussian process regression, okay? What you can see is that as you get closer to the data points, your confidence increases, so the confidence intervals shrink. And the further away you are from any data point, your confidence decreases, so the bars increase. You have a lot more uncertainty. So what's a non-parametric regression problem? It is, given these input-output pairs, ui and vi, infer f star, which would explain, ideally, the relationship between these input-output pairs. We can reformulate this as an inverse problem, which is, as you recall, given y star is equal to g of x star plus epsilon star, infer x star. So what's what here? Y star will be the vector of stacked outputs, the v1 to vn. The unknown x star is the regressor function f star. The forward model G is quite simple in this case. It just tells you, if I give you a function f, evaluate that function at the inputs u1 to un. Okay, so that's your forward map. And the noise epsilon here will be the stacked noise eta 1 to eta n, where the eta 1s, the eta i's are basically the noise here. Sometimes if you're really confident there will be no noise, that's okay. So what are some challenges here? X, the space of possible unknowns, is a function space. Think of it as the set of all functions which pass through your data points. And that's actually, it's not only high dimensional, it's actually infinite dimensional. And the function G, which maps your, it tells you if I give you a function, what are the corresponding evaluations or the values of this function at the input points ui. I hope you can see that that's non-invertible. So if you just go back to this picture alone, there are many functions which pass through this data point, right? In fact, uncountably infinitely many functions. So from that point, this G is actually really badly non-invertible. Okay, so in particular, if it's non-invertible, there's no hope of identifying x star from G of x star. So this is the inverse problem. How do we solve this in a Bayesian way? Well, maybe some of you have, this is like a really fundamental thing. If you consider the coin toss experiment, you toss a coin, you cannot predict a priori what the outcome will be because there are so many variables that go into it, how the coin will land when you catch it, right? And so if there are so many unknowns, what we do is that we model the outcome of this experiment using a random variable. So that's what we're going to do in the Bayesian approach. Since what we want to infer is unknown, let's model it using a random variable x. And whatever we know about the problem that allows us to a priori guess what the outcome will be, let's put that somehow into the prior law, P of x. The next thing is oftentimes you need to assume some known law of the noise. Okay, so in the inverse problem, it's always safe to assume that there's going to be some noise. You also don't know what it is, so we model it using a random variable. A random variable has a law. And for many reasons, people often assume that the noise is Gaussian. This can be problematic, but it turns out that under some assumptions, it actually is not such a problem. So what that implies is that y star is actually a realization of a random variable y, where the random variable y is defined as g of x, the unknown that we use to, the random variable x that we use to model the unknown parameter x star, plus some random variable epsilon. Now here's an important observation. If we know that the random variable x takes a specific value little x, then this model here implies that for any realization epsilon 0, let's say that the random variable epsilon has a specific value epsilon 0, we can rewrite the statement that the random variable y is equal to little y star as saying that the realization epsilon 0 of the random variable epsilon is equal to y star minus g of little x. Okay, so this is just simple algebra. If we know that y star is equal to g of x plus epsilon, we just subtract g of x from both sides. And then we get epsilon 0 on the other side. Why is this important? This is important because now we have a likelihood. We have a conditional law of y given something that we know about the random variable x. Okay, in particular, this likelihood or this conditional probability measure is actually given us for free in some sense from the law of epsilon. Now what we can do is that we can use Bayes' formula, right? Remember, Bayes' formula is equal to posterior is equal to the likelihood divided by the evidence times the prior. We have the likelihood, we have a prior, and since it's really difficult to calculate the evidence, we're going to put it into some proportionality relation, and we get a formula for the posterior. Now, if you might ask, is it okay? Can we do this? Can we just ignore the evidence? It turns out that in many algorithms you can. So if you've heard of Markov chain Monte Carlo, that actually exploits the fact that you can get around, you can avoid having to know what the evidence is. So the key idea here is that we started out with inverse problems, and now we have a Bayesian way of solving this inverse problem. Remember that for the Bayesian, the solution to an inverse problem is the posterior. We started out with an inverse problem given here, and now I've described the Bayesian way to solve it, and the solution is the posterior. It's the conditional probability of the unknown x given the data, given that the data random variable y is equal to the observation that we have in hand, y star. Okay, so that's the solution. For the Bayesian, that is the solution to the inverse problem. I'll just close this part and we can have a break for a moment. Let's just recap what we saw. So this is an inverse problem is of this form. The Bayesian approach is to rewrite or to reformulate the problem using probability theory, using random variables. Okay. What we do is that we first have to choose a prior for the unknown. We have to really think about what information do we have about the problem. Can we use that to design a good prior? And this is really a hard problem. I won't go into it here because there are many, many papers on this, and it's not answered yet, I think. And you need to have a likelihood, basically a relationship that tells you, or a probabilistic way of describing what's the relationship between your parameter, your unknown, and your data. Then, because this is a Bayesian approach, Bayes formula plays an important role. Given the prior and the likelihood, we have the posterior, and that solves our inverse problem. Okay, so there are a few things to take away from part one. How do we describe what we know or our uncertainty about some random phenomena if given incomplete information? We use conditional probability measures. Second, how do we solve inverse problems in a statistical way? There's not just the Bayesian way, there are other ways too, but in the Bayesian way, we do it this way using Bayes formula. Okay, are there any questions? No, then I think let's have a break for 5 minutes. Okay, thanks. Okay, so I think I hope you don't mind having a slightly longer than 5-minute break, but I'll start now in order that we end at around 10:30. So in the second part, as mentioned, I'll really go into more of what this talk is about, randomized Bayesian inference. In the first part, I spoke about Bayesian inference and Bayesian inverse problems. And in the second part, I'll talk about randomization. And this is really where, I'm sorry, I should take this off first. This is really where the theme of the summer school comes more into play. I won't say that it's really close, but it's the closest I will get in this talk. So my apologies if expectations are not met. So this is a picture we saw from the previous part. We have a high dimensional space. In this case, it's actually a space of functions. That's what one is implicitly doing whenever you're doing Gaussian process regression. You're looking in a function space for a specific function. And function spaces are not only high dimensional, but they are infinite dimensional. And you can see this because if you think about a function, how many numbers would you need to describe it? If you just have a function on the closed unit interval, for example, from 0 to 1, and it maps to R, how many numbers would you need to perfectly describe that function? You would need at least countably infinitely many numbers to describe it. Okay. So why are high dimensional problems challenging? Well, first of all, they're everywhere. I argue that in many machine learning problems, you're working in a high dimensional space. And so let's take that as a given. Why are they challenging? They're challenging because the computational cost often grows quickly with a dimension. So let me give an example. Many machine learning problems, and please feel free to correct me if I'm wrong, they involve some kind of matrix vector computation somewhere, right? You're going to be doing linear algebra in a machine learning problem, at least somewhere, I believe. Why? Because you're going to have to solve a linear system of equation. You might want to optimize some differentiable objective function. So you want to compute the derivative, set the derivative to 0 and solve for that equation. Or you might want to do some matrix factorization if you're doing dictionary linear learning, for example. There are many problems where a matrix vector product or linear algebra is important to the problem. Okay. Now, there are many algorithms for computing matrix vector products. So basically here, I mean a matrix M times a vector V and compute the solution W, right? This also includes solving this because you can think of M as the inverse of some matrix. And M here, let's assume for simplicity, M is a D by D matrix. So just computing this matrix vector product, given that M is a D by D matrix, this has the cost, which is big O of d to the 2.87. So it's at least square and almost cubic in the dimension d. And some of you, if you're interested in real theoretical computer science and linear algebra, there's a really nice intersection of these fields where basically they're trying to get this cost down to as low as possible by assuming certain structure, making certain structural assumptions on the matrix M or on the vectors V. But these things only, you can lower the cost basically, but they only work when your matrices are so large that it's for theoretical interest at the moment. What people use often is something known as Strassen's algorithm, and there the cost is big O of d to the 2.87. So this is really the part where I say that high dimensional problems are challenging because they're computationally expensive, right? Especially if you think of d as being millions, well, then big O of d to the 2.87 is going to be really large. And that's just for one matrix vector product. If you have to do this repeatedly, then the cost also grows, right? So how do we have any hope of solving high dimensional problems? We have a hope of solving high dimensional problems because in many high dimensional problems, there's some intrinsic or hidden low dimensional structure, which is then exploited to reduce a problem that's posed in a high dimensional space to the real problem, which is on a much lower dimensional space. So here's a picture. This is one really good example of this is in image processing. Here's a picture of a tree. And this is the original picture. Let's take this as our ground truth, so to say. Now there's an image reconstruction algorithm which produces this picture. And if you switch between the two, you can see there are some artifacts. So first of all, there's a little bit of like smoke, artificial smoke here. There's also artificial smoke here. It's a bit more fuzzy around the tree, right? If you switch from the original to the reconstruction. And here, this is a reconstruction using what is known as 10%. Well, the algorithm isn't called that, but we're representing the image in terms of so-called wavelets. And this picture is basically taken when you throw away everything but 10% of the wavelet coefficients. So what does that mean? Let's compare these two images side by side. This is the original, and this is the approximation. So we can think of this image, an image you can represent by a vector, right? And let's say because it's in a vector, you have some basis of a vector space. Let's just call that basis phi I from I equals 1 to d, where d will be large, let's say on the order of how many pixels you have. Okay, and when you have 1080p or something like this, then it's going to be really large. So we're going to represent the vector x, this image as a vector x, and it's represented by these coefficients xi. So each real number xi multiplies the basis vector phi I. You sum all of these together, you get your original image back. What about the approximation? The approximation x tilde of x with respect to the same basis is basically what you take, we'll call it x tilde. And x tilde has the same, you do it the same way. Basically, you say, what are the real numbers x tilde I? You multiply each with a phi I, you sum all of these, and you get x tilde. So what are the x tilde i's? Well, the x tilde i's are equal to xi for all I in some set calligraphic I, which is a proper subset of 1 to d. Otherwise, x tilde I is 0. So what this means, this is just a mathematical way of saying, we take these d numbers, x1 to xd, we throw away 90% of them. We only keep 10% of them, and we get x tilde. That's the meaning. So in particular, the number of elements in I is basically 1/10 that of d. So you can think of this as 90% dimension reduction. You've reduced the problem of your dimension, construct an image, from a d-dimensional problem to a problem that has dimension d over 10. Okay. So the question is, how do we choose the set I of indexes to keep? Or equivalently, how do we choose which coefficients in this vector space representation of the image? How do we choose which coefficients to keep? And the answer, well, one answer, it's not the answer, it's one possible answer that is has gained popularity in the recent decade, is to use what is known as random embeddings. Sorry. So this is where, in the abstract, I mentioned some powerful mathematical ideas. This is really one of the powerful mathematical ideas. It's known as the Johnson-Lindenstrauss lemma. And the Johnson-Lindenstrauss lemma tells you, let's suppose we have n, capital N points, Z1 to Zn, in some high dimensional space Rd. Let's fix a scalar, or just a number, zeta, which is positive. And in particular, it has to be less than 1. I forgot to say that, sorry. Then the lemma tells you that there exists some constant. And this constant actually doesn't depend on anything. It's what is known as a universal constant. It doesn't depend on your problem. That's part of the magic of this theorem. So there's a universal constant C, such that if we have a lower dimension, little d, which is at least larger than this constant, C, times zeta to the power minus 2, times log n, where n is the number of points you have, then there exists a matrix. So it's a rectangular matrix now. It's little d by big D. So this means that it's basically long and wide, okay? Or short and wide. And in particular, it maps a vector in Rd, your high dimensional space, to a vector in R little d, which is a much lower dimensional space. What this matrix also does is that it tells you if I know what's the distance between the outputs. If I map zi to m of zi, and I multiply zj by m, and I now look at their representations in this lower dimensional space, I measure the distance between these 2 points. Then that distance is bounded from below by the original distance in the high dimensional space times 1 minus zeta, and bounded from above by 1 plus zeta times the same distance for any pairs zi and zj. So I have a whole cloud of points in a high dimensional space. To each point, I apply this matrix vector, I map it to a lower dimensional space, and then I compute the distances in this lower dimensional space. What this tells us is that I've reduced the dimension from big D to little d, where little d is big O of log n. So however many points you have in this cloud. And as you can imagine, typically in high dimensional problems, you don't have as many data points as you do the dimension of your variables. This is not always the case, but in many cases it is so. What's the interpretation of these inequalities? It basically means that mutual distances, so pairwise distances in your original space, are preserved up to an error factor zeta. Okay, so the distances between points in your original space, they get distorted a little bit, but not too much. And the penalty that you pay for this dimension reduction is basically the error rate zeta. So the question is, how do we find this magic matrix M? I mean, in practice, we don't know what this magic matrix M is, and it's really hard to construct it deterministically. But fortunately, if you use random matrices, then with high probability, you can find this random matrix M, or a matrix M that does basically the same job. So the key idea here, and this is really the connection, this is the one point of connection between this talk and the theme of this school, is that randomization can be used to reduce computational cost. In particular, if we go back to the problem of computing a matrix vector product MW equals V, right? We know that that has cost of big O of the dimension, big D, to 2.87. So it's more than quadratic in dimension and almost cubic, right? What we can do is that we can now reduce the dimension by a lot in some cases, right? And by reducing the dimension, you can reduce the computational cost of these matrix vector products. And this computational cost savings gets passed down through the pipeline until you have a really expensive part, I guess. Okay, any questions here? So this result is really cool. I'll just say, because it's really cool, I'll just say a few words about it. The Johnson-Lindenstrauss lemma comes from a really pure area of mathematics. You can call it geometric analysis. And it's also related to probability theory. So it's related to something known as the concentration of measure phenomenon. If you know what that is, great. If you don't, it basically says that in high dimensional spaces, certain random variables are so closely concentrated around their mean, you can almost treat them as being constant. And that's a really high dimensional phenomenon. Okay, so that's it for the motivation for randomization. Okay, any questions about that? No. All right, then we move on to the second part, which is randomized Bayesian inference, the theory of doing this. In the first part, I spoke about how we can do randomization or why we would want to do it. And now I'll talk about how we can combine randomization with Bayesian inference. Okay, so let's change notation. I'm sorry to do this, but I'll sweep this under. I mean, I hope you understand. So we have Bayes' formula from before, right? This is the posterior for the unknown x, given the data is equal to some y star. It's a probability measure on x, and we get it from the likelihood and the prior. I'm going to rewrite the posterior as mu y star as a measure on x, and I'm going to write this quantity here as exponential minus a function phi, which is fixed on a parameter y star and is a function of x, and is divided by some scalar z of y star. And mu is now the prior, okay? So in particular, the superscript y star on the posterior indicates that this is the probability measure that takes into account information in the data y star. The prior is written without the superscript to indicate that we haven't taken into account the data yet. Okay, so mu y star is the posterior, mu is the prior, and phi of x with a fixed y star is, you can call it different things. You can call it the negative log likelihood, or you can call it the data misfit. And I'm going to call it the data misfit here. So the true posterior, mu y star, I'm sorry, is defined as follows. Okay, and we can do a trick which can be made rigorous and kind of treat this as like a fraction. That's the heuristic. I mean, you shouldn't really do it from a mathematical point of view, but you can treat it that way. So we're going to call this, which is the Randomised derivative, if any of you know what that means, as basically this function. Okay. So with this function, if we have this function basically, and if we have the prior, we can always get the posterior from it. And this left-right arrow just means that you can switch from one expression to the other. So that's the true posterior. We spoke about randomization. I'm going to now define a random approximate posterior, mu y star, subscript n. And whenever there's a subscript n, you can think of that as a random approximation with some kind of discretization parameter or approximation parameter n. Okay, and I can basically take the formulas for the true posterior and use them in a similar way to construct random approximate posteriors, whereby now what I'm going to do is I'm going to approximate the data misfit phi with some random function phi n. For this to make sense, of course, I need that this quantity is strictly positive and finite. So here's a question. We have a true posterior, which is what we are interested in, and we have a random approximate posterior. So it's not exactly the same. It's random, first of all, and it doesn't fit the true posterior exactly. So a natural question is, if we do this approximation, how good is this approximation? How good does this random posterior approximate the true posterior? And for this, we need a notion of how far apart measures are. We have two probability measures, mu y star n and mu y star, and we want to know how far apart are they. If the distance is 0, then they're exactly the same. If the distance is positive, then we know that they're different. For this, we're going to use something known as the Hellinger distance. It's a metric. If you're familiar with that terminology, it's a metric on the space of probability measures. And the Hellinger distance between the true posterior mu y star and a random approximate posterior mu y star n, I'm going to write dh, is defined in this way. So it looks like a lot, but just remember that this is a function. I'll go back. So that's this function here. It's just the likelihood up to some normalization constant, and we can do the same for here. Okay, so we take the likelihood, we take the square root, we look at the difference of the square roots of the likelihoods. You can think of this up to normalization constants. That's what this quantity here is. Then we take the absolute value and square it, and we integrate for every value of x against the prior. Okay, then we multiply this integral by half and then take the square root of the whole thing. That's the formula for the Hellinger distance. All right. Yeah, and here are the formulas for the Randomised derivatives d mu y star d mu. So this is the derivative of the posterior with respect to the prior, which is just the likelihood. And we can do the same for the approximate posterior. So some notation, if I write a probability measure nu, and I have which is a probability measure on x, and I have a function from x to r, I'm going to denote the nu expectation of this function by e subscript nu of f, and that's just the integral over x of f of x with respect to nu. Okay, just integrals. Now, why do we care about the Hellinger distance? Why is it useful? We can use it to bound differences in expectations. So if I fix a function x, and I can ask if I have two probability measures, what's the expected value of this same function with respect to each of these two different probability measures? So that's what I'm doing here. What's the expectation of f, any function, with respect to the true posterior, and the difference of that expectation with respect to the expectation of f, the same function f, with respect to the random approximate posterior mu y star n. And it turns out that the Hellinger distance can be used to control differences in expectations in this way. So up to some quantity which depends on f and of course the measures, if I know that this the Hellinger distance is going to 0, then I also know that for suitable functions f, I can also be confident that the expectations are getting closer and closer together. Okay. All right, so with the Hellinger distance, that's what we're going to use to quantify how good this approximation is. There are, of course, many metrics or distances that you can put on the space of probability measures. Some of you might know of the Kullback-Leibler divergence or the relative entropy. That's not a distance, but people do use it to measure how far apart probability measures are. Okay. It turns out that the Hellinger distance is in a sense stronger than the Kullback-Leibler is stronger than the Hellinger, but we're going to work with the Hellinger for now. Yes?
Do you know if there's any connection between Hellinger distance and distance? Higher power,
Wasserstein. Okay, so the question was if there's a connection between the Hellinger distance and the Earth mover's distance or Wasserstein distances. So the Earth mover's distance, if I'm not wrong, is also known as the total variation distance. And the Hellinger distance actually bounds the total variation distance. So if you know that the Hellinger distance is a certain number, then you know that the Earth mover's distance or the total variation distance cannot be larger than that. So control in Hellinger also gives you control in total variation. I forgot what the name of this inequality is, but it has a famous name.
So total variation is stronger.
No, Hellinger is stronger. Because if the Hellinger distances are smaller, then we know that the total variation is also smaller. So control of one gives us control of the other. And Kullback-Leibler in turn bounds Hellinger. So there's, I think that's called the Chisar-Kullback-Pinsker inequality or Pinsker's inequality. For Wasserstein, there is no, for higher order Wasserstein distances, I am not aware of a good relationship between those and the Hellinger distances. But for W1, yeah. Thanks for the question. Any other questions? Yes.
So actually, I was wondering what big phi was in the previous slides and why those accept and participate rather randomized distribution.
Sorry, could you say that again?
Yeah, I'm wondering what is big phi?
Big phi, you can just think of that you have a likelihood, right? To do a posterior, you need a prior and a likelihood. The likelihood is a function. So phi is up to a constant, just log of that function, log likelihood and minus. Yeah. Does that answer your question?
And the y, so what is the difference between that and the y, so the big phi and
I will get to that. I'll give an example, but you can just think of this as, let's suppose that we construct phi n by some randomization procedure. We know what phi is. We have a likelihood. We need to specify a likelihood. We take minus log of that. We get phi. So in theory and in practice, we have a phi. But now we want to approximate phi with some random function phi n. Because, for example, phi might be too expensive to compute. It involves some matrix vector products that we want to make more computationally efficient. So we randomize. And then this randomization propagates to a phi n. I'll give a more specific example soon. Thanks. Okay, so just to recall where we are. Phi n is a random misfit function or a random data misfit. And the randomness of phi n, and this is a key thing, it differs from the randomness in the unknown. You can say that the randomness in the unknown is because we don't know everything about the unknown parameter, x star, that we want to infer. The randomness in phi n is something that we know and that we inject artificially into the problem to get some kind of computational savings. So we can treat these differently, okay? And we are going to treat them differently. The randomness in the unknown can be quantified either by the prior or the posterior, mu or mu y star. And the law of the randomness in phi n is we're going to write it by a probability measure nu n, okay? Because if you think of phi n as a random variable, we know that every random variable has a law. And this law basically tells you everything you want to know about the random variable. So here's a theorem under some assumptions, that I'm going to sweep under the carpet because, yeah, they're kind of technical, but I have them at the end if you're really, really interested. There exists a constant, C tilde, and there exist numbers Q1 and Q2, strictly larger than 1, such that if I look at the Hellinger distance between the true posterior, which is non-random, and a random approximate posterior, So this Hellinger distance is also going to be a random quantity, right? It's a function of a random variable. So in turn, it itself is going to be a random variable. I can then take the expectation of this. So you can think of this as like, this left-hand side is like the mean square error in the random approximate posterior with respect to the true posterior, MSE, mean squared error. Or in this term here, yeah, I'm taking the square root, but you get what I mean, I hope. I can bound this error in the posterior up to this constant C tilde by this somewhat complicated looking expression. So I'll walk you through it. First, we take the absolute value of the differences between the data misfits. Phi here is the true data misfit, and phi n is a random approximate misfit. And this is what we hope is going to be computationally more efficient to work with instead of phi. We take the absolute value of this, take the absolute value to the power q1. And now because this absolute difference depends on phi n is a random variable, we want to get rid of the randomness. So we take the expectation, okay? Then for mathematical reasons, we take this expectation to the power q2 over q1. And then finally, because this function still depends on x, so the unknown variable, we then take the expectation over the prior, which is a probability measure on x. And then again, for mathematical reasons, we take 1 over q2. So if you're familiar with LP spaces, we're basically just taking LP norms with respect to first the randomness in the approximation, and then the randomness in the prior or the unknown. Why is this important? We can now use it to answer the question of how good is this approximation. So we don't want to answer how good is the approximation for a single random posterior, because typically you'll have many random posteriors, right? If you have a random variable, you never just sample one value of that random variable. You try and get an understanding of how is this random variable distributed, and you do that by Monte Carlo. You take many samples and try and look at the sample mean, for example. So that's why we take the expectation here. What this theorem tells us is that this approximation is as good as the approximation of your data misfit. Okay, that's the interpretation of this inequality, up to some constant C tilde and up to taking averages. So if you recall, the key idea from the first part is that for a prior mu, a likelihood phi and a negative likelihood phi and a data y star, the posterior can be formulated as a function, as the output of a function called Bayes, and we give the inputs mu, phi, and y star. What's the idea of part 2? The key idea is that this function, if you fix mu and y star, so if you fix the prior and the data, and you allow the likelihood or the negative log likelihood to vary, it turns out that this function is continuous. Okay, and continuity is actually very nice because I spoke about inverse problems in the first part. One thing that makes inverse problems complicated is that if you perturb one of the inputs, if you perturb your data just a little bit, the resulting inference for your unknown parameter can change by a lot. And this is not good heuristically, because you would like to hope that if you change some parameter of your problem just a little bit, then the solution of your problem should also change not too much, right? But that doesn't happen in inverse problems. What I'd like you to take away from this section is that when you do Bayesian inference, actually you do have this nice property whereby if you change something, one of the input problems a little bit, the resulting solution of the problem also changes by not too much. And in fact, this inequality tells you that you have some control over how much it changes if you know how far apart you perturb your input. Okay. All right, so now in the remaining 10 minutes, I'll speak about an example, and this will give hopefully an idea of how we would construct this random approximation phi n of the data misfit. And I'm referring to this as the randomized misfit method of Le et al, and I'll show the references at the end. So let's look at a concrete example. We have an inverse problem with a standard Gaussian likelihood. What does this mean? So recall that if our data is given as y star is equal to g of x star plus some realization epsilon star, sorry, there's a star missing, of a random variable epsilon, and we know the law p epsilon of epsilon, then we know what the likelihood looks like, right? It's just given in this equation. We saw this before. So let's make this more specific. Let ID be the d by d identity matrix. Now let's assume that epsilon, our observational noise, is standard Gaussian, a d-dimensional standard Gaussian random variable. then we know, hopefully all of you know, that the law of this Gaussian is up to some proportionality constant is equal to exponential minus half z transpose the identity inverse z, or just norm squared of z. Okay, that's just this is just a fancy way of writing norm squared of z. It generalizes it a little bit if you're interested. So we can plug this formula in to this formula for the likelihood, and we get this quantity here, where phi is actually just equal to half the difference between the data y star and your prediction of what the observation will be. So the prediction here is g of x. Take the transpose of this vector, multiply it from the left by the inverse identity, which is thus the identity, and then multiply from the right by the same difference between your data and your prediction. Okay, so that's what the formula for phi is in this specific case, where we assume that the observational noise is a standard normal d-dimensional Gaussian random variable. All right? Okay, so now let's pick R to be a RD valued zero mean random variable such that its covariance matrix is the identity. Okay, and I'll show you an example of such a random variable in a minute. Now let's take capital N copies of this random variable, R superscript K. Now let's go through a bunch of calculations. For every, let's fix X and Y star. So X is our like predicted input or our predicted unknown, and Y star is the data. Phi of X and Y star is given as this. This is what we saw from before. And remember that here, the matrix that we have in this, in the data misfit is just the identity, right? And since we assume that R, this random vector, has the covariance matrix equal to the identity, I can replace the identity with the covariance matrix of R, right? And now in the next, really the approximation step, I'm going to replace or approximate the covariance matrix, expected value of R transpose, with a sample mean. Okay, I take n samples, IID copies of the random vector R. I actually sample what their values are. I construct these, the rank 1 matrices, I sum them and divide by n. So you can think of this as just a simple Monte Carlo approximation of this covariance matrix, of this expected value. Okay, and now using linear algebra, look, you have a transpose of a vector, it multiplies another vector, and by symmetry, you can actually show that this quantity here is equal to this. Okay, and now I'm going to call this quantity the random approximate data misfit phi n. Why n? Because we're taking n copies of the random vector x. And why is it random? Well, because each R superscript k is a random variable. Okay. So just to recap, phi n for a fixed y star is a random misfit depending on random vectors. And it approximates the true data misfit because we're doing Monte Carlo. And you know from the law of large numbers, well, the whole reason why Monte Carlo works is that we have this law of large numbers. If you let capital N grow large enough, then this quantity here will converge in some sense to what you started with before. So what's an example of such a random vector R? And I'm going to use this as, I'll call this like a random sparsification method. Let's fix some positive number S and let R be a random vector with components R1 to RD, where each entry is IID and has this distribution. It's equal to square root of S, this positive number, plus 1 with probability 1 over 2s, minus 1 with probability 1 over 2s, and 0 otherwise. Okay? So you can hopefully see that if S is really, really large, then each entry is going to be either plus 1 or minus 1 with probability 1 over S. So that's going to be really, really small, close to 0. And therefore, this entry is going to be 0 with really high probability. So the interpretation of this is the larger S is, the more likely R is going to be a sparse vector. Now recall that we approximated our true data misfit, which was just like a square, right? The square of the difference between the data and your prediction of what the output should be. We're going to replace it with this approximation here. So for each, for a fixed y star in x, like this difference in between the data and your prediction of what it should be, we multiply it by this sparsifying vector. But each vector is different because it's an IID copy. So each time we compute these things, we're not going to get the same number. What are some properties of phi n for this random sparsifying R? We have dimension reduction. Think about this. What is the action of Rk on this difference y star minus g of x. It basically says I'm going to throw away most of the entries of this vector. I'm going to set it to 0 because you're multiplying by 0, right? And I'm only going to I'm going to look at the collective action of only a small subset of this vector. So in that sense, we're doing dimension reduction because we're throwing away a lot of the entries in the difference y star minus g of x. Okay. On the other hand, it's also highly parallelizable because you can just sample many RKs. And for each RK, you can farm it out to each of your processors and compute what's this difference, take it all back, sum, and you get phi n of x and y star. Okay. And these are properties that are really, how should I say, common to many randomized numerical linear algebra methods. You get some kind of dimension reduction, and they're highly parallelizable. So recall under some assumptions, we had this control over the distance in our posteriors, given if we can control the distance in the data misfits. We can apply this result to this random sparsifying R. In particular, the left-hand side, we can bound using a really explicit quantity, which is namely some constant c divided by the square root of n, where nu n is the law of this random data misfit. And in fact, it's given by the law, the joint law of these random vectors. And c here, I'm writing it here because I want to illustrate we can't completely get rid of dimensionality. C depends on the dimension, the original dimension of your problem. It also depends on your parameter s. How much do you sparsify? Okay. And it also depends on the prior. But we know we can't get around this because this bound here definitely depends on the prior, mu. So some remarks, you can show from this bound that the distance goes to 0 as n goes to infinity. As you take more and more copies of R, the sparsifying vector, this quantity is going to go to 0 at the rate 1 over square root of n. And in general, hopefully you see that we can't improve this rate because fundamentally what we're doing is that we're using a Monte Carlo approximation. And if you're doing Monte Carlo, you know it's hard to get better than the rate of 1 over square root of n if you don't have additional assumptions. We're at the end here. Let me recapitulate the key ideas. In part 1, we said, I hope what you take away from that is that whenever you're doing inference of some kind, implicitly you are working with a probability measure. It represents what you know about the problem and what you know about your solution after you have incorporated data. One way of doing this update in your state of knowledge is using Bayes. So whenever you do Bayes, you have to work with a prior and a posterior. This has problems of its own. It's not always easy to construct a prior or to construct a likelihood, but if you can, then you can do Bayes. And the other thing is that the posterior it depends in a nice way on your prior, likelihood, and data. So for part 2, I hope I've persuaded you that randomization can reduce computational cost. Sometimes it also increases it. So you have to really balance how much does it cost to do the randomization? Do you still gain something, of course, at the end? But you can use it to find some low dimensional intrinsic structure in a high dimensional problem. Second, for a fixed prior and data, the output of your Bayesian inference procedure depends in a nice way on your data misfit or your likelihood. And the key takeaway is that there is potential for reducing the cost of Bayesian inference by using randomization. So here are some references. So just to briefly mention, so this paper is really about introduction to compressed sensing. If you haven't heard about it, it's really one of the success stories in the 2010s, for example. It really reduced. So if you're familiar with MRI or any CT scan, you're passing radiation through a patient. This is also harmful, right? And before compressed sensing, it turned out that people thought that you needed to do lots of scans. So you needed to send a lot of radiation through the patient to get a good resolution. With compressed sensing, it turned out that you can reduce the number of scans by a lot. And the idea of compressed sensing really works on this Johnson-Lindenstrauss lemma. It's really closely related to that. If you're interested in randomization for numerical linear algebra, I can recommend this paper by Halko, Martensen, and Trop. It's a nice review paper, really focusing on randomized numerical linear algebra. The randomized method, if you're interested to see how does this random sparsification perform for a PDE problem, you can look at this paper, and the bound is presented in this paper, which was joint work with Tim Sullivan and Aretha Teckentrup. And with that, thank you very much for your attention.
Right, thank you for the nice talk.
Thanks.
Other questions?
Thank you. So how sparse can you make those random projections to retain the approximation guarantee? So I guess if it's about concentration of measure, it should break at some point.
I don't have a good answer for how one could see this from concentration of measure. Because, yeah. So instead, I'll try and answer your question through here. So the rate is always going to be 1 over square root of n, right? And S here, the larger S is, the more sparsifying these random projections are. So you're doing much stronger dimension reduction heuristically, right? If you make S very large, you'll always have the rate 1 over square root of n, but your constant is going to blow up. So there's always a trade-off. You can sparsify, you can do really strong dimension reduction, but you'll pay for it in the fact that the convergence will be slower in some sense because the constant will be much larger.
Okay.
Yeah. There's, of course, I mean, your question is good because, of course, there is no perfect method. Every method will have its advantages and disadvantages, and there's no way of getting around it. Yeah.
Sure, there's always this trade-off between accuracy and
exactly.
and compression or
accuracy or efficiency.
Speed, efficiency.
Yeah. Exactly.
Right. Okay, thank you.
You're welcome. Thanks for the question.
Okay. Are there more questions? Slowly go down.
I think it's time for coffee.
Okay, that gave you enough time, and I saw you also asking questions during the lecture. So, yeah, let's thank the speaker again.
Okay. Thank you.